Okay, so moving on to part 4. So we're looking at 2015. Part G, copy the structure of the aspirin molecule into your answer book and draw a circle around the carboxylic acid. So this one should be easy enough. Carboxylic acid is always COOH or C double bond OOH. So there is your carboxylic acid group. A rectangle around the carbonyl part. So a carbonyl part is always C double bond O. So there is your carbonyl group. So a fairly easy one in question 4G. So continuing on with 2015, then we're on to question 8. And we were asked to study the reaction scheme below and answer the following questions and give the IUPAC names for A, B, and C. So if we start off with the first one, which is A, which is C3H6, you have a couple of options. You might spot, first of all, that this is in the format CnH2n. And if it's CnH2n, the CnH2n is, of course, the formula for the alkenes. And it's a 3-carbon alkene. So if it's 3-carbon alkene, you're looking at propene. Otherwise, what you could do is you could draw it out. So we need 3 carbons and 6 hydrogens. So if we draw 3 carbons, the only way of getting 6 hydrogens around this is if there's a double bond. So we have to put a double bond here, a single bond here, and then 2 hydrogens at the end, 1 hydrogen here, and then 1 and 1 and 1. And again, that gives you propene. On to the next one, which is molecule B. So we'll put in here that that is propene. Of course, this can also be called proponene because the double bond is on the first carbon. The next compound then, we have CH3CHO. So now something like this I would just draw out straight away. So start with your CH3, then you move to your CHOCHOH. So sometimes students will say to me, they see CHO and they wonder, okay, is that an aldehyde? When the reality is it's not, because if it was an aldehyde, you would always have the CHO at the end of the molecule. So for example, you would have something like CH3, whatever it might be, CHO. The CHO would be at the end. That would indicate an aldehyde. Whereas here, it's in the middle. So because it's in the middle, it's actually not CHO. What it is CH, and then there's an OH. Now, normally this OH is in brackets, but in this example, it's not for some reason. So we just have to try and adapt. So we're going to CH3CH, so we pop in our H there, and the OH then is attached to the CH. So your OH group is going to be here. And then we've got a CH3 then at the end. And once you have that, then you can pretty much see what you have. We've got 3 carbons. So we're looking at prop, and we've got an alcohol group on the second carbon. So this is propanol, but you have to say where the alcohol group is. And it's on the second carbon. So this will give you propan, 2-ol, which is normally the way I write it, but they can also be written as 2-propanol. Either way is perfectly acceptable. And then finally the third one is CH3COCH3. So again, this CO here in the middle, this is going to be a carbonyl group. So working on that one, we're going to go with CH3, which is this, and then C double bond O, and then CH3 to finish it off. And this one here with the double bond O in the middle, of course, is a ketone. So again, it's prop, and it's propanone. Also, you can say propan 2-on if you want here as well. Propan 2-on. But the reality is that double bond can't be anywhere else. If that double bond was here at the end, double bond O is at the end, then this would become an aldehyde. So that's really the only place you can put it. But either way is perfectly acceptable. Moving on to part B then. Name the addition polymer formed from compound A. So if we scroll back up and have a look at A. So A is propene, and it's asking for the addition polymer. So if you have propene, multiple propenes, you end up with polypropene. And polypropene is also called polypropylene. So polyprop, P-R-O-P-Y-L-E-N-E. And both of those are acceptable, whichever one. Part C then, identify the bonds broken and the bonds formed in conversion Y. So let's go back up and have a look at conversion Y. So what have we got here? Looking at these, what I would do then above these is write in what each one is. This is a ketone, as we found out, and this one here is an alcohol. Now, what type of alcohol it is important. Is it a secondary alcohol or is it a primary alcohol? Because that has an effect on what the conversions are. Now, looking at this alcohol here, you look at the carbon that's connected to the OH group, which is this, and how many carbons is that attached to? So it's attached to one carbon on the left and it's attached to one carbon on the right. Therefore, this is a secondary alcohol. So if we go back up to the question, what we actually have here is a secondary alcohol. This is important because when a ketone goes to a secondary alcohol, we have this conversion, which is Y. And that's what the question is asking us. So Y is a reduction. Now, we don't need that just yet because this question asks us about which bonds are broken. So if we have a look at it, look at these two compounds here. We're being asked, how does this compound at the bottom, how are the bonds broken, what bonds are broken, and what bonds are formed? So obviously you can see here that the double bond O, that double bond is broken. And when that double bond is broken, an OH bond is formed up above it, and also a CH bond is formed. Let's go down and look at this in slightly more detail just to explain. It's enough to just say what bonds are broken, but more detail might be needed here for further questions. I'll just draw a quick sketch and I'll be back in 1 second. So here's your quick diagram. So I've just drawn out the ketone here on the left, and it's been reduced to the secondary alcohol, so I've just reversed it around and moving from left to right this time. So if you were to identify what's being broken, so what most students do is they say, well, this is being broken, okay? This is being formed, and then also you'll notice there's nothing here underneath this C on the left, but there is a bond here to a hydrogen there. So what a lot of students will do is they will write down C double bond O is broken. They will say an OH group is formed, and they will also say a CH bond is formed. And that is almost a perfect answer. However, you need a little bit of information, extra information, for the C double bond O. Remember, in a double bond, so when you have a C double bond O, in a double bond, these two single bonds are not equal to each other. The top single bond, or well, one of the single bonds, is called a sigma bond, and the bottom bond is called a pi bond, always in a double bond. You might recall that in nitrogen, which was a triple bond, you had a sigma and a pi and a pi. So when C double bond O breaks, it's the weaker one that breaks. And of course the pi bond is the weaker bond. So the pi bond breaks. And that's what the question is asking you about. You also need to put that in any answer you give. A C double bond O is broken, and you need to put in C double bond O pi bond is broken. Because you don't refer to just the double bond. You have to say which part of the double bond, and it is that part. The sigma bond doesn't break, so you can't just say C double bond O breaks. You have to say which part of the bond. So that's a slight distinction there and something to be careful of. So moving on to part D, an isomer of compound B can be synthesized from an aldehyde. Name the isomer of compound B and the aldehyde. So let's just try out our aldehyde and we'll be back in a sec. So here's compound B. It can be synthesized from an aldehyde and it wants an isomer of this compound. So normally with isomers, what we say is if you knock off a carbon and it's H3s and you put it somewhere else, that's normally what we do for isomers. That won't work here, and this is why. So what we have is, if you knock off that carbon at the end and introduce a CH3 group, and you have your OH up at the top, what you'll notice is you still have 3 carbons in the longest chain. So the 3 carbons, of course, in the longest chain is still going to give you prop. The OH is still on the second carbon, so this is just going to give you propane 2 all again. All right. So in that circumstance, this won't work. So the actual best way to do this is actually if you just move the OH group. So if you move the OH group, you again still end up with the isomer being this. And again, all your carbons surrounded by hydrogens. This is different because, of course, this is propan-1-ol, which is a different compound, or just propanol. So that's the isomer. Remember, same amount of carbons, hydrogens, oxygens, same molecular formula, but different structural formula. The last part of that says then it can be synthesized from an aldehyde. You're asked to name the isomer, which is done, and the aldehyde. So propanol, if that's being synthesized from an aldehyde, the only aldehyde it can be is propanal, which is your aldehyde. And then it asks you, I think, to draw the structure as well. So if you want to draw the full structural formula for propanal, again, 3 carbons with a C double bond O and a H at the end for your aldehyde, and make sure all carbons are surrounded by 4 hydrogens. So that's your aldehyde there. How can the aldehyde be converted into B? So how can the aldehyde be converted into B? So you have an aldehyde being converted into an alcohol. And this is an example of a reduction. And this reduction then is involved with a nickel catalyst and hydrogen molecule. They're your 2 options. If you're wondering where this is coming from, this is all in the revision notes. So if I go back to my revision tab here, this is the first video that I sent out. And as you can see here in this particular part here, you can see the ethanol is being reduced via hydrogen and nickel to the ethanol. So again, it's fairly repetitive. Let's move on to the next question. This is part E, and this is the end of it. So the boiling points of compounds A, B, and C are minus 48, 56, and 82, so they're increasing, but they're not necessarily in the, okay, they're not in that order. For each compound, identify its boiling point, justifying your answer in terms of intermolecular forces. So what I'll do is I'll just draw out the molecules, and I can point at it then for you. So let's have a look at these. So this first one here, this is going to be your alkene. So when you're actually talking about which ones have the lowest and highest boiling points, it can often be a case of elimination. So first of all, let's see what bonding is between them. So when you have an OH group, you're going to have hydrogen bonding. Hydrogen bonding is a very, very strong bonding, requires a large amount of energy. And that's because of this OH group. In other words, when this compound is attracted to another of its own compounds, there's hydrogen bonding between the OHs of the molecules. The one at the end then, your ketone, this exhibits dipole-dipole bonding. And again, fairly strong force, but nowhere near as strong as hydrogen bonding. And then finally at the start, then we have our alkene. And alkenes have got the weakest bonding. And the weakest bonding here are what's called van der Waals forces. So what we've got now is van der Waals forces, which is the weakest. So this is the weakest. This one here is the strongest bond, and this one here is in the middle. So when you actually look at your temperatures that you're going to need to boil it, your temperature is a measurement of how much energy you need to put in to break it. So obviously when you look up at this, you're looking at hydrogen bonding at 82 degrees Celsius. It's going to take that. The lowest then is going to be this one, which is minus 48 degrees Celsius. And then finally the one left in the middle is 56 degrees Celsius. So that covers each compound, its boiling point, and justifying your answers in terms of intermolecular forces. On to 2014 question 10 for the next video.